From the smallest particles to the largest celestial bodies, the universe is in a constant state of motion. Understanding how objects move is fundamental to comprehending the intricate workings of our world. This is where kinematics comes in. It is the branch of physics that describes the motion of objects without considering the forces that cause the motion. In our exploration of kinematics, we will encounter three key concepts: position, velocity, and acceleration. Position refers to an object's location at a particular time. It tells us where the object is. Velocity, on the other hand, describes how quickly an object's position changes over time. It tells us how fast and in what direction the object is moving. Finally, acceleration measures how quickly an object's velocity changes over time. It tells us how the object's speed and direction are changing. Imagine watching a car race. Each car's position on the track changes with time. Some cars move faster, overtaking others, indicating a higher velocity. When a car speeds up to gain a competitive edge, it's accelerating. These concepts are crucial for analyzing motion in various scenarios, from the trajectory of a ball to the movement of planets. As we delve deeper into kinematics, we'll uncover the relationships between these fundamental concepts and learn how to describe motion with precision and clarity. From the graceful arc of a basketball to the movement of planets in our solar system, understanding motion is key to unlocking the secrets of the universe. To understand the language of motion, we need to grasp the interconnectedness of position, velocity, and acceleration. These three concepts are intertwined, each providing a unique perspective on an object's movement. Position pinpoints an object's location, answering the question, where is it? We can represent position using coordinates on a defined system, like a number line or a three-dimensional grid. Imagine a person walking along a straight path. Their position at any given time tells us their location on that path. Velocity, on the other hand, goes beyond location to tell us how fast an object's position is changing. It combines speed and direction, answering the question, how is the object's position changing over time? If our person walks 3 meters to the right every second, their velocity is 3 meters per second to the right. Acceleration delves into the changes in velocity. It tells us how quickly an object's velocity changes over time. It answers the question, how is the object's velocity changing? If our walker starts from rest, accelerates to a velocity of 2 meters per second over 2 seconds, their acceleration is 1 meter per second squared. This means their velocity increases by 1 meter per second every second. By understanding these three concepts, we can paint a comprehensive picture of an object's motion, from its starting point to how it changes speed and direction over time. In our everyday language, we often use the terms distance and displacement interchangeably. However, in physics, these terms have distinct meanings. Understanding the difference is crucial for accurately describing an object's motion. Distance is the total length of the path traveled by an object. It doesn't consider the direction of motion. Imagine a car driving from point A to point B on a winding road. The distance traveled is the total length of that winding path. Displacement, on the other hand, is the overall change in the object's position. It is the shortest distance between the initial and final positions, regardless of the path taken. In our car example, displacement is simply the straight-line distance between points A and B. To illustrate further, imagine a runner completing a lap around a 400-meter track. The distance covered is 400 meters as they ran the entire track length. However, their displacement is 0 because they end up back at their starting point, resulting in no overall change in position. This distinction is important because it highlights that motion isn't just about how much ground an object covers, but also about its net change in position. When analyzing motion, we often encounter two types of values, instantaneous and average. These values provide different perspectives on an object's motion, allowing us to understand both the details and the bigger picture. Instantaneous velocity refers to the velocity of an object at a particular instant in time. It's like taking a snapshot of the object's motion at a specific moment. Think of a speedometer in a car. It shows the car's instantaneous speed at any given time. Average velocity, on the other hand, represents the overall rate of change of position over a specific time interval. It doesn't consider the variations in velocity that might occur within that interval. It's like looking at the car's journey from start to finish and calculating the average speed based on the total distance and time taken, regardless of any speed fluctuations during the trip. The same concepts apply to acceleration. Instantaneous acceleration captures the rate of change of velocity at a specific moment, while average acceleration provides the overall change in velocity over a given time interval. Understanding the difference between instantaneous and average values is crucial for analyzing motion accurately. It allows us to examine both the fine details and the overall trends in an object's movement. Section 5. Equations of motion, unveiling the secrets of uniform acceleration. In the realm of kinematics, understanding motion with uniform acceleration is fundamental. Uniform acceleration refers to motion where the object's velocity changes by the same amount over equal time intervals. To simplify the analysis of uniformly accelerated motion, physicists have developed a set of equations known as the equations of motion. These equations provide a powerful toolset for solving problems related to uniformly accelerated motion. They connect the key variables of motion: displacement, initial velocity, final velocity, acceleration, and time. Here are the key equations of motion. 1. Final velocity equals initial velocity plus acceleration times time. This equation relates the final velocity of an object to its initial velocity, acceleration, and time. 2. Displacement equals initial velocity times time plus 1/2 acceleration times time squared. This equation connects the displacement of an object to its initial velocity, acceleration, and time. 3. The square of the final velocity equals the square of the initial velocity plus 2 times acceleration times displacement. This equation links the final velocity of an object to its initial velocity, acceleration, and displacement. These equations are incredibly versatile and can be applied to a wide range of scenarios. For instance, we can use them to determine the stopping distance of a car under constant braking, the time it takes for a ball to reach its highest point when thrown vertically, or the velocity of a rocket as it accelerates into space. By understanding and applying these equations, we unlock the ability to predict and analyze the motion of objects undergoing uniform acceleration. Section 6. Uniform versus non-uniform acceleration. While uniform acceleration simplifies our calculations, real-world motion often involves changes in acceleration. Understanding the difference between uniform and non-uniform acceleration is essential for accurately describing more complex movements. As we've learned, uniform acceleration means the velocity changes at a constant rate. A car cruising at a steady speed on a straight highway exemplifies uniform acceleration. Its velocity remains constant. Non-uniform acceleration, however, implies that the rate of change in velocity is not constant. This means the object can speed up, slow down, or change direction at varying rates. Imagine a car navigating a busy city. It accelerates, decelerates, and turns, resulting in non-uniform acceleration. Analyzing non-uniform acceleration often involves calculus and more complex mathematical tools. Instead of relying solely on the equations of motion, we might use graphs, slopes, and areas under curves to represent and analyze the changing acceleration. Recognizing the difference between uniform and non-uniform acceleration allows us to choose the appropriate tools and approaches for analyzing and understanding the complexities of motion in various scenarios. Section 7. Projectile motion, a dance of gravity and inertia. Projectile motion is a captivating example of motion under constant acceleration due to gravity. It describes the motion of an object projected into the air and subject only to the force of gravity. Understanding projectile motion is crucial for analyzing the trajectories of objects like baseballs, cannonballs, and even rockets in their initial stages of flight. The key to understanding projectile motion is to recognize that it can be broken down into two independent components: horizontal and vertical motion. The horizontal component of motion experiences no acceleration, meaning the object moves at a constant velocity in the horizontal direction. Conversely, the vertical component experiences a constant downward acceleration due to gravity, which affects the object's vertical velocity. The combination of these two components results in the characteristic parabolic trajectory of projectiles. The object moves forward horizontally, while simultaneously being pulled downward by gravity, creating the curved path we observe. The shape of the parabola depends on the initial velocity and the angle at which the object is launched. Understanding projectile motion unlocks the ability to predict the range, maximum height, and flight time of projectiles, showcasing the power of physics to describe and predict the motion of objects in our world. Section 8. The impact of air resistance. In our previous discussion of projectile motion, we made a simplifying assumption that air resistance is negligible. While this assumption holds true for slow-moving objects over short distances, in many real-world scenarios, air resistance plays a significant role in shaping an object's motion. Air resistance, also known as drag, is a frictional force that opposes the motion of objects through the air. It arises from the collisions between the object's surface and the air molecules. The magnitude of air resistance depends on factors like the object's shape, size, speed, and the density of the air. The presence of air resistance introduces complexities in the analysis of motion. It affects both the horizontal and vertical components of projectile motion, leading to shorter ranges, reduced maximum heights, and altered trajectories. For instance, a baseball hit with the same initial velocity will travel farther in a vacuum than in the presence of air resistance. Understanding air resistance is crucial for designing airplanes, cars, and even sports equipment. By minimizing drag, engineers can improve fuel efficiency, increase speed, and enhance performance. Section 9. Kinematics in Action Real-World Applications. Kinematics, the study of motion, might seem like a theoretical concept confined to textbooks, but its applications are vast and impact our lives in countless ways. From the technology we rely on to the sports we enjoy, kinematics is at play, silently shaping our world. Consider the automotive industry. Engineers rely heavily on kinematics to design cars that are both safe and efficient. By analyzing motion, acceleration, and impact forces, they can develop crumple zones that absorb impact energy during collisions, braking systems that provide optimal stopping power, and aerodynamic designs that reduce drag and improve fuel efficiency. In the realm of sports, kinematics plays a crucial role in analyzing and improving athletic performance. Coaches and athletes use high-speed cameras and motion sensors to track the movement of runners, swimmers, and ball players. By analyzing these kinematic data, they can identify areas for improvement in technique, optimize training regimens, and gain a competitive edge. The field of robotics also relies heavily on kinematics. Engineers use kinematic principles to design robots that can move with precision and dexterity. Whether it's a robotic arm used in manufacturing or a surgical robot assisting in delicate procedures, understanding motion is paramount for their successful operation. These examples highlight just a glimpse of the vast applications of kinematics. From everyday technologies to cutting-edge scientific advancements, the principles of motion are woven into the fabric of our modern world, demonstrating the power of physics to explain and influence the world around us.